Hello everyone, welcome to lesson 2.10 from Precalculus, which is all about the inverses of exponential functions, also known as logarithms. So let's dive in. So the big idea for this lesson is the fact that logarithms, which we got introduced to last lesson and you probably were introduced to previously in Algebra 2, are defined in this class as the inverse of exponential functions. So let's explore this idea a little bit. So if we start off with a function f of x equals b to the power of x, then I'd hope you agree with me through our conversion that we talked about last lesson, that this means logically that x is equal to the log base b of f of x. So this means that f inverse of x must equal log base b of x, because when we take an inverse, we switch the x to f inverse and we switch the f of x to x. So by this design, we have created what a logarithm is, which is the inverse of an exponential of its same base. So it means that those functions, logarithms and exponentials, are inverses as long as they have the same base, and it doesn't matter which order. So we can say that an exponential is the inverse of a logarithm, or a logarithm is the inverse of an exponential. So what does this mean graphically? This means for us that the equation y equals log base b of x is a reflection of y equals b to the x over the line y equals x. That's just how inverses work graphically, right? What this also means is that the domain of an exponential function, which is negative infinity to positive infinity, now becomes the range of a logarithmic function, and the range of an exponential function now becomes the domain of logarithmic function. So the logarithmic function is a little weird. It has a domain of 0 to infinity non-inclusive and a range of negative infinity to positive infinity, which means that logarithms are kind of like your even roots in that fact that you cannot have negative numbers, but you also cannot have 0 inside of a logarithm. And that makes sense because, again, if exponentials raising things to a power, you're never going to have 0 as a result, and therefore, if you can't have 0 as a result, and the inside of logarithm is the result, you can't have a 0 there either. And yes, we're talking about functions, and we've been talking about functions, but it's important to remember that logarithms can also be used as operators, and exponents are also used as operators. So those operators, if you will, undo each other if the bases are the same. So diving into that, that means b to the power of log base b of x is x. Those would cancel each other out, the b and the log. In addition, log base b of b to the power of x is x as well, because those operations undo each other. So let's dive into question 1 here. So this question is asking us to, 1, determine if f is an exponential or log, and then to write the coordinates of its inverse. So how do we do this? Well, we know in exponential, if the x's increment by the same amount, that the f of x should be proportional, should be multiplied by the same number. Well, the opposite should be true for logarithms, where the input should be proportional multiplied by the same number, and the output should be incremented by the same amount. So depending on which one we have, depends if we have an exponential or a logarithm. So if we look at this first function here, we go from -1 to 0 to 1 to 2 to 3. The x's are incrementing by 1. The f of x's look to be multiplying by 3. So this would be exponential. That's ugly, but you get the idea. It's exponential because the outputs are proportional to each other. If I look at the second function here, the x's are growing by a factor of 4, and the outputs, the f of x's, are incrementing by, in most cases, 1, but I don't know, I think I messed that up. I think that's supposed to be a 3. 4 to the third power, 16 times 4. Yeah, I definitely messed that up. That is definitely a 3. But you get the idea there, right? And if they give you the information, you can also use the domain and range of functions and your knowledge thereof to help you with this. If I look at this function here, I see a negative number for the input. If my only options are exponentials or logs and I have a negative as an input, it's got to be an exponential because negatives can't be an input for a logarithm. And vice versa, I see that I have both negative and positive outputs for a logarithm, so that would mean that that can't be an exponential because the exponential is always above 0. Now again, there is shifting that could happen. We could be taking these functions and shifting them left and right and up and down, which would change that idea. But we really haven't gotten to talk about those yet, but I digress. You can tackle these problems in a couple of different ways, but the proportionality of the input or the proportionality of the output is what we're really looking for here. And as far as the points of the inverses, you're really just flipping what you have. Oh, it might help to actually flip the values. Not bad. Proving things are inverses. We've done this before, and I told you that composition is the way that we really do that. So what we're going to do is we're actually going to do f of g of x, and then we're going to do g of f of x, and hope to get x as a result from both of those. So let's start with the f of g of x. So we have 2 to the power of log base 2 of x. Now, I already told you before that the operators would cancel, but let's play around with this. Let's say that this is equal to y. If I have an exponential here, I can rewrite this as a logarithm. That would be a log with a base of 2 and a result of y is equal to its exponent, which is a log base 2 of x. And because logarithms are one-to-one functions, the only way for log base 2 of y to equal log base 2 of x is if y is equal to x, which means this whole thing here is equal to x. Perfect. It works. Let's do it the other way. So this time we have log base 2 of 2 to the x power. And the same kind of way, I'm going to set this equal to y for now. And we have it as a logarithmic equation. We can rewrite it as an exponential, and that would be 2 to the power of y is equal to 2 to the power of x. Exponentials are also one-to-one functions, which means the only way for this equation to be true is if y is equal to x. So y is equal to x, which means the f of g of x is also equal to x. So in both cases, we got x from the substitution, or this composition, if you will, which means that these two functions are indeed inverses. Very cool. Last but not least is we're going to find the inverse of the following functions. So like we did before, we're going to change the f of x to x, and we're going to change the x to a y temporarily. We'll change it to f inverse later. And we would divide by 3, so x over 3 is equal to log base 5 of y. You have to get the logarithm alone first before you convert, so that's why we divided by 3. Once we convert, we get 5 to the power of x over 3 is equal to y, so f inverse of x is equal to 5 to the power of x over 5. Not bad. Same idea for g. We are going to do x is equal to 10 to the power of y divided by 6, which means that we now need to convert this to a logarithm. So this would be the common log of x is equal to y over 6. I would multiply by 6, so 6 times the common log of x is equal to y, which means that f inverse of x is equal to 6 common log x. Not bad. That is really it for this lesson, really exploring the relationship between exponentials and logarithms and the fact that they are indeed inverses. If you have any questions, please make sure you ask. Otherwise, I'll see you in the next video.